Hello, everyone. My name is Krishna Reddy. I'm a professor of civil and environmental engineering at the University of Illinois in Chicago, USA. My presentation is modeling coupled dynamic processes in landfills, holistic long-term performance management to improve sustainability. Before I get started, I want to thank the conference organizers, in particular Professor Atullah for inviting me to present this keynote lecture. I also want to thank my doctoral students who have contributed to this research. I also want to thank funding agencies for providing the financial support, and in particular, U.S. National Science Foundation provided 2 grants to support this research. So in my presentation, I will give you a brief introduction to landfills and bioreactor landfills, and what research that we have done on landfills in the past. And then I will give you an overview of how we developed this new coupled thermo-hydro biomechanical model. And I'm going to talk about how it was validated based on the reported lab, field, and modeling studies, and then how it is applied to full-scale landfills and bioreactor landfills, how the research results are used for practical purposes. And then at the end, I'm going to talk about conclusions and broader implications on sustainability. So the landfills are now well-engineered structures. These are designed as per RECRA 40 CFR Part 258 subtitled regulatory requirements in the US. It consists of a bottom liner, side liner, leachate collection system, and the final cover system. And the final cover system, prevents the infiltration of precipitation, and the leachate collection system at the bottom, removes all the liquids that have been generated in the landfill. So relatively, the waste and the landfill inside is relatively under dry conditions. So there has been a lot of monitoring data for over 3 decades or so, and all that data shows that the landfills as engineered and constructed are performing quite well. Then what is the issues with the engineered landfill then? The problem is that inside the landfill, it is relatively dry, waste is relatively dry. So you have a slow waste decomposition, and that results to low gas generation and low settlement rates, and that leads to prolonged waste stabilization period. And you need to keep monitoring it and associated costs with that. And the leachate treatment and disposal costs associated with this one in the long run, and increased methane and carbon dioxide emissions. And this is a long-term liability issue that needs to be addressed. So to address these problems, the concept of bioreactor landfills came into existence. Bioreactor landfill is nothing but subtitled de-engineered landfill. As I explained before, it has liner systems, leachate collection system, and final cover system. And in a conventional landfill scenario, you take out the leachate and send it to a wastewater treatment plant. And in this case, wastewater, the leachate collected is stored and then re-injected into the waste, into the landfill using the trenches and vertical wells, so that you are enhancing the moisture content of the waste. And that will lead to rapid waste degradation, and provides the higher rates of gas generation and increased gas to energy conversion, high settlement rates, and therefore it reaches stabilization much early. It also provides a reduced post-closure monitoring costs, reduced organic shrink of the leachate, which makes it easy to treat, reduced leachate treatment and disposal costs, landfill space reclamation for fresh waste. And if you are doing landfill mining, you will be able to reclaim a lot of inorganics through that. So even though this bioreactor landfill concept is very attractive with all these benefits, there are some key practical challenges. How do you design these leachate injection systems? Trenches and vertical wells and drainage blankets are commonly used. What should be their spacing? What should be the injection pressure or flow rate? So that is a practical issue. And how do you ensure the slope stability while injecting the leachate is an issue. What are the consequences on gas, heat, and leachate generation when you are injecting the leachate? How the spatial temperature variations in moisture, settlement temperature, and properties of the waste occur, and how do you ensure the stability and integrity of the liner and cover systems that generally consist of geocomposite systems, and how do you predict the time for waste stabilization? So these are all the practical concerns. So in order to address these practical concerns, you really need to have a good understanding of these coupled dynamic processes that happen in landfills. If you think about the waste as inert solids and biodegradable solids, and the pore space could be filled with landfill gas and landfill leachate. And when you inject the leachate, you're going to create these different processes within the landfill. So hydraulic processes that control the leachate and gas flow, moisture distribution, liquid and gas pressures, biochemical processes that controls the microbial activity, solids loss, gas generation, and leachate characteristics, thermal processes that control the heat generation, heat transfer, and heat loss, and the mechanical processes that control the deformation, strain, stresses, constitutive behavior, and strain. So in fact, all these processes are interrelated, and they are spatially variable and temporally changing. So these are dynamic processes and coupled. And understanding these is very important to answer all the questions that I mentioned for bioreactor landfills. So we have been doing the landfill research at UIC for the last 2 decades or even more. And we conducted several field investigations. We went to the landfills and did boreholes and collected the samples from different depths, characterized those wastes for index properties and biochemical properties. And we did extensive geophysical investigations to monitor the leachate recirculation and in situ moisture conditions, and also look at the changes in the properties, including the dynamic properties. We also conducted several series of lab investigations to look at the biochemical properties of the waste, leachate chemistry. We created controlled anaerobic reactors and degraded the waste at different levels of degradation, and then conducted the testing to determine the hydraulic properties, shear strength properties, and compressibility properties. Then we embarked on numerical modeling in a systematic way. And eventually, our goal was to develop thermo-hydro-biomechanical modeling. So I'm going to present this numerical modeling effort that we have been undertaking for almost, as I said, almost a decade or more. So our goal was to develop this new coupled thermo-hydro-biomechanical model. So in the beginning, we were focused on flow modeling or hydraulic modeling, and this effort was undertaken by my PhD student, Hanumat Kulkarni. His PhD thesis title is Optimization of Leachate Recirculation Systems in Bioreactor Landfills. The goal was to develop a two-phase flow so that we can predict the leachate recirculation in the landfills and come up with some design guidance for leachate recirculation systems. We developed the two-phase flow model. It assumes that we have 2 phases: leachate as a wetting fluid, and landfill gas as a non-wetting fluid. We assume that Darcy's law is applicable for defining the flow of these 2 fluids. And capillary pressure and relative permeability are assumed to be the functions of saturation, and they can be expressed by Van Gogh function. And biodegradation is neglected during this initial stage of our modeling. So these equations provide you the relative permeabilities of wetting fluid, that is leachate, and non-wetting fluid, that's gas. So effective saturation is defined by this equation, and then the relative permeability of these liquids and gases are going to be controlled by these variations in relative permeabilities. So Darcy's law for multi-phase flow with the phase pressures causing each fluid to flow, they are given by these governing equations. And applying the constitutive laws and then combining with fluid balance, you get these equations. So you have these equations that can be solved for pressures and the saturations. In fluid flow only modeling cases, this term is omitted. And if you really want to consider mechanical coupling with hydro, that term needs to be accounted for. And in this case, you use a mechanical model, but in this model, you consider the effective stress that changes due to the changes in the pore pressures. And you use a constitutive model and calculate the strains. So during the initial stage of our modeling, we did some hydromechanical modeling for using the more Coulomb failure criteria for model validation purposes wherever there was deformation monitored. But most of our initial modeling was focused on flow only modeling. So once we developed this two-phase flow model, we try to validate with reported laboratory studies. This is Hudson 2004. They had this huge cell. They filled with municipal solid waste and then applied the loading. They measured the compression as well as the moisture content. So we modeled this one and we compared the results with experimental results, and reasonable agreement was seen. And then Oliver and Burke, they did a test on this using the square tank, 1 meter by 0.98 meters. And initially they added leachate and then they loaded it. And we were able to, predict the same as that observed in the experiments. Capillo and De Castro, they did some leachate injection experiments into the waste. They had big columns like this, 300 centimeters by 60 centimeter internal diameter. They injected the leachate on the top, and they were able to measure the moisture variations along the depth using the neuron scattering technique. And we modeled that one, and we were able to predict the volumetric moisture contents with depth reasonably well compared to the experimental results. Staub also, did large-scale experiments, lab experiments. They injected the leachate for 30 days to saturate the sample, and then they allowed it to drain. And they looked at the moisture content changes in the sample, and we simulated the same thing using the model, and we were able to predict the results similar to the experimental results. So in addition to the lab experiments, we validated our model based on the field studies. Hire and Hyder, they did a field study on a landfill using permeable drainage blanket, using scrap tires as a drainage medium. And we modeled the same thing, and we found out that the distance that is covered by this injection as monitored was 25 meters, and then our model gave 23.5 meters. So it's a reasonably in a good agreement. We also validated the model with previous modeling studies. McGreener used the Sutra for modeling the flow. And we did the same thing with our model and were able to compare the results reasonably well. And Hyder and Thierry did modeling with Hydras 2D, And he applied for the horizontal trench scenario, vertical well scenario, and drainage blanket scenario. And we did exactly the same thing. And then we were able to, predict the results similar to their predictions. So that really gave a confidence that our flow modeling is reasonably well. And so all these results, numerical formulation and validation, are published in these two papers. You can find more details about how we did this. And then a validated model was used to evaluate the effectiveness of these different leachate injection systems, as I mentioned, trenches, vertical wells, and drainage blankets, which one are more efficient. So that comparative study was done using this model, and results are published in this paper. And then we used the model and did a parametric study and developed design charts for vertical wells, design charts for horizontal trenches, design charts for drainage blankets. And we also created design charts for selecting the minimum setback distance from the side slopes to avoid any slope stability problems. So after we did the hydraulic modeling, the next phase of modeling was done by another PhD student, Raju Giri. His thesis title is Coupled Hydrobiomechanical Modeling. And in this, the goal was to combine biological aspects with the hydromechanical modeling that we did in the first phase. So the flow modeling or hydraulic modeling is exactly the same thing that we looked at it. And in this one, we are focusing more on mechanical aspects. So it's important to consider appropriate constitutive model. The simplest model is Moore Coulomb, and we applied that to predict the mechanical response. And then the way you combine the hydromechanical is due to changes in the pore pressures and corresponding changes in the effective stress, and calculating the strains as a result of that. Now, in this phase, we wanted to include mechanical modeling as well as biodegradation model. And for biodegradation, we use the UIC-based LandGEM model that considers the first order decay kinetics. And it can predict gas production. And based on that, we can calculate the mass loss in organic solids. And in this, this is the equation that is modified for gas generation. We included the decay constant changing with moisture content. And as you can see by this factor, water factor, F water is included in this one. And that relates to the effective saturation that I mentioned before. So with this incorporation in the model, we were able to predict the gas production, and we can calculate the amount of methane, and we can keep track of cumulative methane produced, and then we can, also calculate the maximum methane potential based on the biochemical methane potential. And taking the ratio of that could define the DOD, degree of degradation, and the degree of degradation was related to the properties of the municipal solid waste, unit weight, hydraulic conductivity, anisotropy, shear strength, and moduli, based on our extensive lab tests that we have done in previous years. So this is how the now coupled hydrobiomechanical modeling was implemented. You have your injecting leachate, you have a hydraulic modeling two-phase flow that gives you the moisture content and pore fluid pressures. And then we take that one, look at the biodegradation modeling and mechanical modeling. So as you see, these three are coupled, and if needed, we can calculate the factor of safety for the slopes. And then we implement this one with the different time increments. So this model implementation is presented in this paper. For more details, you can look at that one. And then this model, we try to validate with available lab results. Staub et al. Did this large-scale column experiment, and they applied the loading in increments. and they measured the displacements and the moisture content. So we modeled exactly the same in our numerical model and compared the lab experiments with model results. So we found reasonably good agreement. We also compared our model results with a field scale study that was done by Bioreactor 2012. They implemented this field scale lysimeter at a landfill. They evaluated physical, chemical, biological response of municipal solid waste during leachate injection. So the leachate injection was done from day 399 for total duration of 1,047 days. And they had data on unit weight with the depth and also moisture content with depth. And we were able to, model that, and the results are not exactly the same, but pretty close. Same thing, we were able to predict the peak outflow flux with time, and our model seems to slightly underpredict outflow from this. Whereas time-dependent compressions state for different loading conditions seems to match reasonably well with the field data. Once the model is validated, we try to apply it to a real landfill case. So this is the cross-section of a landfill, Orchard Hills landfill in Davis Junction in Illinois, close to Chicago. So we modeled the bottom liner, side liner, and the leachate collection and removal system, and then also the final cover. And we had these horizontal trenches for leachate recirculation. And most importantly, the details of liner systems are captured in this modeling, and also details of the final cover also captured in this modeling. So we simulated the leachate injection, and we try to understand how the waste is responding, the settlement, gas generation, and the liner response were able to be understood. And we did different parametric studies to understand, what are the controlling system variables for this one. So all this coupled hydrobiomechanical modeling phase for the framework and validation are presented in this paper, and systematic evaluation of large scale or real landfill scenario was presented in this paper. And then, as I mentioned, the system effects, we varied leachate injection rates, spacing, all those things, understood how they will affect the overall Bioreactor landfill performance. Those are presented in this paper. And at the end, we, this waste properties are highly variable because of the heterogeneities. So we did a reliability assessment of the landfill performance. So this is the third phase of our modeling, and this is done by another PhD student, Girish Kumar. His goal was to combine the thermal effects into the model. So now, before we had hydrobiomechanical model, but combining the thermal aspects, we wanted to truly develop this coupled thermal hydrobiomechanical model. So, so initially we were focused on, how to incorporate thermal effects into the existing model. So we collaborated with Cal Poly researchers, Professor Jim Anson and Dr. Nasli Essler, who have monitored and modeled thermal aspects of landfills extensively. And in this, heat transfer through conduction is considered using this equation, and the volumetric heat generation rate from biodegradation of the waste is expressed by this empirical equation. And at the ground, the temperature variations are expressed by this equation. And rate of methane gas production was estimated using this equation. And then in this equation, the waste degradation rate, K value is is defined as a function of saturation and the temperature and defined by this equation. So the temperature actually, affects the biodegradation of the waste by using this equation. And the model was validated to predict the temperature at different depths from surface all the way, deep into the landfill. And the model predictions are found fine. And then with the modeling, we were able to understand the effects of temperature on gas production, and the settlement, and other landfill performance parameters. And all these results are presented in this paper. You can find more details on this one. But we, thought that a lot of our previous modeling efforts are based on empirical approaches, and we wanted to take a fundamental approach to model these different processes. And we developed a new biochemical model, developed a new thermal model, and developed a new constitutive model, and then integrated all those models into the two-phase flow model. And now, we have a rational coupled thermo-hydro biomechanical model that can be applied in general. And then we validated this model based on the available lab experiments. And then we applied this CT-HPM model to predict the performance of actual landfills and bioreactor landfills in a holistic manner, including the liner and cover system performance. The two-phase flow model is the same as what I described earlier. Basically, it's a multi-phase flow in unsaturated soils. Leachate is one fluid and landfill gas is another fluid. Both are assumed to exist as the two immiscible fluids. And then we apply this balance of mass, Darcy's law, fluid constitutive laws, relative permeability, capillary pressure law according to Van Guchten model. And then we were able to predict the flow of these two phases in the landfill. That's similar to what we have done in the previous phases. The biodegradation model, before we were using the Landgem model, more of an empirical approach. So instead of that, we used this two-stage anaerobic digestion model proposed by McDougall. And in this one, we considered, advective and diffusive processes are not, important. And degradable solids is assumed to be composed of cellulose. And there's evidence that the cellulose mainly contributes to the, the degradation and gas evolution. And then two-stage anaerobic digestion, as defined by McDougall, was considered in this modeling. And the first phase, first stage includes hydrolysis and acidogenesis and acetogenesis, creating the acids. And then in the second phase, methanogenesis, that generates the methane and the CO2. So this process can be expressed by this reaction and the stoichiometry. And the main parameters that are involved in this are C, M, and S. C is for volatile fatty acids, and then methanogenic biomass and solid degradable fraction. And the rate of change of those are defined by these equations. And RG, RH, RJ, and RK, these are all the rate constants defining these different rate kinetics. And based on the stoichiometry, gas generation rate was calculated. And then based on consideration of enthalpy, heat generation rate is calculated. So again, as you see, gas generation is based on this biochemical considerations, and heat generation is as a consequence of this methane. As a result of gas generation. So this avoided the use of any empirical approach for thermal or biological model. So In thermal model, the anaerobic digestion, as I showed you previously, that generates the heat. We consider conductive heat as the main mechanism for heat distribution. Balance of heat, energy, specific heat capacity, Fourier law, heat conduction equations are shown here. And the temperature affects this microbial growth rate. And we consider that as the function of the temperature. And that temperature dependency varies depending upon temperature. Some lab studies have defined how it varies, and based on that, this function is defined. And these functions at different temperature ranges, capture the observed rates in the experiments. So that's how the temperature and biodegradation are coupled. So more detailed information is available on this coupled biochemical and thermal modeling in this publication. Then we went into mechanical modeling. As you saw in previously, we used more Coulomb theory, but degradation is accounted by varying the properties as a function of a DOD in an empirical manner. So instead of that, we wanted to implement a good constitutive model. And in this model, we consider the total strain as elastic and viscoplastic and biodegradation induced settlement strain. And then, this plastic strain itself, considered as the combination of rate dependent and rate independent strains. So basically elastic and plastic and viscoplastic, and then biodegradation induced strains. So that's how we assume that the total settlement consists of. And then we use the soft soil creep constitutive model for calculating the elasto-viscoplastic strains in this study. So elastic strains are given by this equation. They are a function of the stress as indicated by this equation. And the volumetric creep strain rate is given by this equation. In this, we have the equivalent pressure calculated by this equation. And then creep induced hardening is expressed by this equation, and general creep strain assumes the normality condition and expressed by this equation. And then this is the cap type yield surface that's given by this equation here, the failure surface Fs, and then tension cutoff are expressed by these equations. And biodegradation induced strain is calculated based on the framework that McDougall and Pyra developed. And this is based on the assumption that biodegradation induced strain depends on the changes in the voids, as well as the changes in the degradable solids. So this is the governing equation we use in this model. The whole model implementation, like a stress calculation algorithm, is shown here, and it's implemented in our model. So the details of elasto-visco bioplastic mechanical modeling are provided in this publication. You can look at it for more details. Now we have a fluid flow model, we have a biodegradation model, we have thermal model, we have a mechanical model. And they are all like interlinked, and they need to be coupled. And, they vary spatially and temporally. So there's a complex, interdependency and the dynamics. And all these are captured in our model implementation. You can find more details about how all these different modules have been integrated in this paper. So now we have this new coupled thermohydrobiomechanical model, and is there any data that we can use to validate it? So there are a few more lab studies that are done in a more detailed manner, looking at all the biochemical aspects and gas generation. So one study was done in the US with the landfill waste collected from different landfills. There's one study that is done in UK, and they did this long-term, large-scale lab experiments for different durations. So this figure shows the study by Fay and Zekos at the University of Michigan. And then this figure shows the schematic of large-scale lab experiment that is done in UK. So in Fay and Zekos experiments, they didn't apply any vertical stress, or they have a negligible vertical stress, whereas in the UK study, they applied different normal stresses and looked at the response of the waste and biochemical characteristics. So using the model, we predicted and compared with the experimental results. As you see here, solid degradation fraction, volatile fatty acids, this comparison seems to be, pretty reasonable. Methanogenic biomass, that is not measured in the experiments, but you can predict using the models. And this is the landfill gas generation. As you can see, it matches with some experiments. It doesn't match with some other experiments, perhaps due to the fact that we assumed only the cellulose contributes to the degradation component. And so maybe we are underestimating the biomass that is biodegradable, or even the waste that is used in the cells may not have been properly modeled. And in the UK experiments, they did the test under different vertical stresses, so they were able to measure the deformation, and we matched that one. It compares quite well. So now that we have a reasonably validated model, we applied to the large scale or real landfill scenario, like the one which I showed you before. And we simulated a conventional landfill, and also we simulated bioreactor landfill. So bioreactor landfill basically involves leachate injection. We assumed continuous injection. Injection pressure is 50 kPa, and we assumed 4 trenches as shown in this figure. And the horizontal spacing between the trenches is assumed to be 30 meters. And with the model, we were able to predict the spatial and temporal variations of degree of saturation, pore water pressures, as you see from here. We were able to understand how leachate recirculation was affecting the maximum wetted area and pore pressures. If you look at the pore pressures along this cross-section AA, we can see that pore pressures near the slopes are not high, so therefore we don't have any issues with the slope instability. This model was able to predict spatial and temporal variations of all these biochemical parameters: solid degradable fraction, volatile fatty acids, methanogenic biomass concentrations. As you can see, in conventional landfill, the changes happen slowly, but in bioreactor landfill scenarios, you see the changes happening in a more faster way. And as you see, near the top, you don't have much effect because you don't have favorable conditions, temperature or moisture for biodegradation to occur. And you can, as we define the degree of the degradation, and you can see how the waste is degraded based on this parameter, and it in bioreactor scenario, it really degrades really quick compared to the conventional landfill scenario, as you see from here. And you can also calculate the methane, total methane gas production. And you can see in a bioreactor landfill scenario, you have a higher gas production compared to the conventional. And the stabilization time is defined as the time that it takes to evolve most of the gas. So in bioreactor landfill case, the stabilization period is roughly 12 years, whereas in conventional landfill, 33 years. So that shows the advantage of using the bioreactor landfills. And since we have a thermal components model, thermal model is included in this model, you can look at how the temperature changes in the landfill. As you see, that elevated temperatures happen in the middle of the landfill. And in case of conventional landfill, you could have a temperature, with the depth under different times is shown here. You can see you will have a less temperature compared to in the bioreactor scenario. You can actually see, how the maximum temperature changes in the landfill with time. You could have as much as 60, 65 degrees in the bioreactor landfill compared to only about 40 degrees in conventional landfill. The maximum heat generation rate also can be seen here. In the bioreactor landfill, it's high, whereas in the conventional landfill is low. So you can also understand the evolution of the settlement through this coupled model. We're showing the L1, L5, L10. L1 is the lowest layer, L5 is the middle layer, and L10 is the upper layer, because we assume that waste is placed in layers. You can monitor the settlement in the short term, see how the temperature changes, and in the long term, how the settlement changes with time. And then here it's only viscoplastic. Here we're looking at biodegradation into settlement. Here we're looking at a visco-bioplastic settlement. As you see from here, if you look at the last layer for bioreactor landfill case, the settlement occurs really fast and and more. And compared to the conventional landfill, settlement rate is low and overall settlement is slightly less. So we're able to capture this evolution. You can also, look at how it changes with time and spatially. You can look at the entire deformation characteristics of the landfill through this model. And you can see that wherever we are injecting the leach at those locations, the settlement is much more than other locations. So the differential settlements could be important in bioreactor landfills. One important aspect of our modeling is to be able to predict the response of the liner system, bottom liner system and cover system as the waste degrades. So there is interaction between the waste and the liner and cover systems. So we were able to capture that one through our modeling. So these results show how the temperature in the liner, side liner, base liner are changing in case of conventional and bioreactor landfills. As you see in case of bioreactor landfills, the temperature are higher, and as a result, you can see how the displacements are induced in the liner. In case of conventional liner, you have higher displacements compared to the bioreactor landfill system. Actually, if you have a higher temperature, it is shown that interface strength is higher, and so as a result, you can see the less settlements or deformation that's happening in a bioreactor landfill. So we use this model after studying one particular landfill. We wanted to make good use of this landfill, and we did a systematic parametric study. We varied the injection pressures, injected spacing, injection mode, continuous versus intermittent. And we considered the different spacing and different configurations. And we developed some recommendations for practitioners for designing these leachate recirculation systems and operational conditions. So you can find that information in this publication. And when you are dealing with the landfills and waste, one of the biggest concern is heterogeneity. So in modeling, you probably use one set of parameters, but these parameters vary quite a bit. As you see, the parameters vary, depending upon the waste type, depending upon the location in the landfill. So we wanted to see how heterogeneous conditions in the waste are going to affect our performance parameters. And we did this Monte Carlo simulations assuming variability in the model input parameters, we found out that anisotropy and void change parameters are the most critical parameters compared to all the other parameters. And with this one, we were able to simulate different variable scenarios through Monte Carlo simulations and compared with typical deterministic analysis. And we found out that, the difference between the stochastic and the deterministic analysis. So we found that the deterministic analysis slightly over-predicts the results compared to the probabilistic or stochastic based results. So these results are summarized in a publication, and you can look at more details in that. So overall conclusions, we developed this new model that overcomes the key limitations of the previous models, and accurately models these coupled processes. This is reflective of our more than 2 decades of our research effort. Model is validated with the reported lab, field, and previous modeling studies. Of course, more validation would be useful. And key trends in the evolution of waste characteristic, gas generation, temperature, and settlement and liner response was able to be captured. The model can be used to, simulate a realistic full-scale conventional landfill or bioreactor landfill operations. And this will allow us to optimize the system variables, leachate injection well spacing, injection quantities, pressures, and mode, which is much needed for practitioners. And it ensures the landfill and bioreactor landfill safety and allows the prediction of the stabilization time. This is important for regulators. They want to know how long, how fast it could stabilize so that the environmental threats are minimized. Overall, this modeling and the bioreactor landfill approach could contribute towards the sustainability. So we can have a safe and effective solid waste containment, not only containment, but we are also treating the waste biologically. So we are happening biotreatment simultaneously with the containment. And with that one, you are ensuring short-term and long-term environmental protection of air, land, and water. And with the predictable gas and temperature generation, you can consider the energy recovery projects. And faster stabilization could allow mining if needed, or allow the end use of the landfill for some beneficial purpose. And there are a lot of economic benefits by bioreactor landfills and optimizing it through this modeling approach, leachate treatment, post-closure monitoring, land reuse, etc. And the community engagement and environmental justice, I believe, can be accomplished by this because these are well-controlled engineered systems with no environmental impacts, and there is that beneficial uses in terms of energy recovery and faster stabilization, mining, and reuse of the site. And a lot of dump sites are in in areas of underrepresented people. So, environmental justice can be accomplished in a real sense. So that's our project briefly, and I went over, at high level without giving a lot of specific details, but I mentioned those publications. You can look at those things for more technical details. If you have any questions, you please feel to contact me at this email address. And you can connect me to Twitter, Facebook, LinkedIn, and you can go to my these websites for more information on publications and additional information. I greatly appreciate, again, listening to me. And also I want to thank again the organizers for giving me this opportunity to present. So thanks everyone.